the presentations, you learn something new even in basic presentations, but the hallway track is just indispensable.
The first talk I gave on ranges was in 2019 at this conference. And the world was in a very different state with respect to the ranges and range implementations. The committee had just finalized the first ranges paper and basically had said, this is what C++ 20 ranges are going to be. Of course, we're in 2023, and ranges have evolved greatly in 2023, and I'll tell you they're going to continue to evolve in 2026. But I want to open your thinking about ranges a little bit, because ranges are not just the stuff that's in the ranges namespace in the standard. They're much more than that. They're a fundamental abstraction that we're starting to use and leverage, and I'm going to show you that right from the get-go. I'm going to show you a lot of code today. Everything's going to be linked to a Godbolt, so when you get the copy of the slides, you can go there and play yourself. This is a tutorial in the sense that I'm trying to get you guys bootstrapped with ranges to some degree. So I'm going to give you some insights into it. I'm not going to be the one that's going to tell you every potential pitfall. There's no possible way to do that in a 1-hour talk. So let me just get a survey of the audience here. Who uses STL algorithms? Okay, pretty much this entire room. Who is already using ranges? That's a smattering of people. And are you using ranges with C++20, or are you using like range v3? I should ask range v3. Now, oh, one back there. 2, maybe 3. Okay, so basically, we don't have a lot of adoption yet, which is interesting. So maybe this talk will help spur that. So the beginning of began and end. That's one of the key things I think is going to happen with ranges. So slide 3, here's code. This is how you write sort in C++ 98 up till 2020. Nothing fancy. Here's sort the ranges way. And you'll notice that, we've gotten rid of the begin and end. We don't need begin and end because we take a range to the sort algorithm now. There's something more interesting on this slide, though. What's this last line? Anybody know? Print. Your mind is blown, isn't it? One line of code here, std print, not just a random print, std print. That's C++23, valid code. You can now write those 3 lines of code and make that work. That is a revolution, and ranges makes that happen because you can use a range to print, and it knows what to do. It knows how to do the right thing. And that's not in std ranges, that's just in the standard library. All right, let's do something different. Let's do our classic lookup. We need to find something that's in a collection, right? So we have a predicate that checks to see if my integer value is 6. I use send my began end to find, and I have auto I. What do I get back here? Anybody? An iterator, yes. That is correct. So I have to check it against n to find out if the iterator is valid, to dereference, and then I dereference it. Again, nothing surprising here. The ranges version of this is basically the same code. So we don't fully get rid of iterators in all of the cases. Iterators are still a thing in C++. And in fact, ranges is built entirely on top of iterators. And So we'll see a little bit more about how that is coming up. So, once again, no begin end. Those are gone. Now here's something completely different. And if you ask ChatGPT, like I did actually, this is what ChatGPT thinks the ranges library is all about, views. And, you know, it might not be completely wrong about that. But the reality is that the vast majority of the ranges library is new algorithms. It's not actually views. I'm not going to say that you shouldn't use views. In fact, I'm here to convince you otherwise. But in any case, this is a radically different way of doing things, right? I'm doing something very different here. I have an auto thing that's called divisible by 3 that constructs a filter and a predicate there. And then I do some kind of bar syntax down here, pipeable. I'm doing piping. So I guess the mothership has landed and we don't know what has happened to C++ anymore. This is just a very different way of thinking about it. So to get comfortable with that takes a little bit of time, and it takes a little bit of understanding about how the library is built. I hope to do that for you today. So first part of the talk, we're going to go over basic range information concepts. Then we're going to do all of the range algorithms, every single one of them. Nobody's laughing. You guys are like deadpan. There's like 200 of them, guys. We can't do them all. We're going to, look at a couple of them, and we're going to look at what makes the ranges algorithms different than STL algorithms. That's the important thing to know. And then we'll look at the range views. That's where we'll probably spend the majority of the talk. And then we'll look at a few other things, some adjuncts that are important to know about. Okay, range basics. 4 key terms. Range. What is a range? It's something that can be iterated over. So that's nothing surprising. This has been an idea in C++ for a very, very long time. A range algorithm, also not a new idea. It's an algorithm that takes a range as its input or its output. The view part, this is where things start to get more interesting. It's a lazy range that's cheap. And I'm sure there's a few of you in the audience that meet this description. Lazy and cheap, that is. But really here, what we're talking about is cheap to copy, cheap to assign. So we want to be able to pass views around in cheap ways. And then range adapters are a thing that allows you to take a range and make it into a view. And this is where that pipe syntax comes in. So range adapters, a lot of people think about as the primary thing that's new and very, very different. And why is that different? It's going to be different because of composability. Algorithm composability is something that the STL does not do terribly well. So let's cover some mechanics first. Basically, C++ 20 and beyond, you're basically going to have an include called ranges. Many of the things don't actually need this include because they're actually in algorithms. But there's ranges, sub namespace, and there's ranges views, and then there's a shortcut to the views called std views. So why is it like this? Why, did we have to put all of this extra stuff here? Why did we not just dump all of this in std and call it a day? Well, it's because the ranges algorithms themselves are not really fully compatible with the STL algorithms. And that will be evident when we start talking about some of the details. So as a result, and by the way, this was a terribly long discussion to figure out how to do this, and people didn't like this solution and so on and so forth. But here's what it is. It gives you a path to migrate to these when you want to, and it works. Now, in this talk, I'm going to shorten std ranges to RNG all over the place, in part because, I have slides here and you guys want to be able to see stuff. But I also do that in code that I write professionally because it just makes things shorter and more obvious. You can come up with your own name and shorten it yourself. So we're going to see what all of these things mean in a little bit. All right, so diving deeper into what's a range, it's a pair of iterators, a begin and an end. But one important thing is changed in ranges, and that is that the end type and the end type iterator and the begin iterator do not need to be the same type. They just need to be comparable. And that gives us some very interesting capabilities that were not present in the STL as a result. This is one of the non-backward compatible changes. Now, as it turns out, there are still good reasons why you'd like to be able to use some of your STL algorithms even with ranges. So David Olson, who's sitting in the front here, I'm going to call him out, is responsible for making the change that allows that to actually happen. So one of the big things in doing this work was making it all compatible in a way. It's not perfect, but it's as compatible as it can be. So the Sentinel is the end iterator, and that can be a different type. So that's something important to know. So what are some examples of ranges? Well, they're all over the place, right? I mean, all of your containers are ranges. All of your container adapters are ranges. But anything that you can put together some iterators for can also be a range, and you can use these range algorithms with them. By the way, I should mention that I'm showing you sort taking a range, but it's still, these algorithms also still take a pair of iterators because sometimes you might want to have a subpart of a range, or you might want to use something that isn't a range inherently because it's a regex iterator or something like that. String and string view. String's a container. String view is an interesting thing. We'll talk about that a little bit later. Who's using string view in this room? A lot of people. Okay. Span and MD span. Who's using span? Okay. Not too many. I think maybe I have to ask the question, who's using C++20? Anybody? Yeah, not bad, not bad. Okay, so span is a C++20 thing. We may talk about that if we have a little bit of time at the end. So there's many libraries, of course, outside the standard, that also model ranges. So here's an example. Here's Boost Flatmap. Anybody use that? Well, there's going to be an STD one now soon, but implementations are slow to come. So here's a flat map of string and ints. Put a couple of values in it. Of course, it's a map, so it's sorted naturally, right? So I put them in reverse order. They come out standard order. By the way, STD print works on maps too, out of the box, because of the ranges. And this is why it's not just about what's in ranges namespace. Ranges as a concept is very important. Now in this next part, I construct a reverse view. So there's view ideas back again, and I can reverse the range. I didn't actually have to move any of the data in the range to do that. I didn't have to print it the way I did it here, but I printed it this way because I wanted to show you that with structured bindings, I can get the key value out of that map, and I can do the print on it individually if I want. I could have written the same line of code that I wrote above, and things would have come out reversed. Okay, so let's dig in on algorithms a little bit. As I already said, they're a little different. They're not always a drop-in replacement, depending on what the algorithm is, which, again, we can't possibly go through them all. But one of the important properties to think about with algorithms, if you haven't thought about this, is that all algorithms execute immediately, right? You call the algorithm, it iterates over the range that you've passed it, whether it's iterator pair or an actual range. The iteration is controlled by the algorithm. It's not controlled by your application at that point. That's very different than what we're going to talk about with views. Views are the other way around. You control the iteration, and the view does the calculation at your demand. Other two important things. The return values are different for new algorithms, and oftentimes you'll see, we'll talk about that on another slide. And there's this idea of projection. So projection doesn't cover all of the algorithms, but many of the algorithms have the ability to project. So, well, there's the list. It's not the whole list. It doesn't fit, actually. Those are the range-enabled algorithms in 2x. And you'll notice that I've put a 23 next to the ones that are 23. So there were a smattering of them in 23, but the vast majority of these are in C++ 20. You should recognize almost every name on this list. So if you don't like views and you don't like the things that they do, or you don't like something about it, what you should take away is, well, guess what? I have all these algorithms that at least I don't need to type begin end, for one thing. And by the way, very might well be possible that they're better in some significant way because they offer some different features that those STL algorithms didn't. So all of this should be very familiar. But there's one big difference. And all of these algorithms are specified with concepts. I think everybody probably knows what concepts are by now. They're a mechanism to constrain algorithms, constrain templates, and you can overload on these constraints. So this brings the important ability for overloading on the constraints. Maybe it's going to give you better errors, maybe it's not. But in general, what I've seen is it's as good or better, depending on the particular algorithm. So that's an important difference. And, you know, as mentioned, they have some different features. This ability to project is something that comes from the Adobe source libraries, which is an STL-like extension or library from a long time ago. And basically, this allows you to get a predicate to something while your algorithm is executing. So here's an example of sort. I have a structure. In that structure, I have two members. If I just use less, the normal less, it's going to do the comparison of both members, right? So what if I just wanted to use one of the two members? Well, I can either go off and I can write a comparator function, do something like that. But in this case now, I can just pass the projection directly to the sort algorithm, pass it and tell it to use the IDX. And it will sort it using IDX only. I mentioned that there's improved return values. So one of the very important things about the design of the ranges algorithms is they try to live to the principle of not discarding information that needs to be calculated as part of the actual algorithm. The STL algorithms were not great about this. In a lot of cases, you would have to do something and then you would throw it away. Now, there are explicit use cases for throwing data away. Like, for example, if I calculate whether a range contains some value, I've calculated the position, more than likely, in that range of that value. If I don't give you an iterator back, I've thrown away information. But contains is specially named, so you know you're throwing away information. That's different than some of the other ones. Find last is a very interesting example because find last is a new algorithm in C++ 23. And as it turns out, this is something that Boost has had for a while. It's called find backward. And anybody ever try to, do stuff with reverse iterators? It's really complicated. It's really complicated, as it turns out. It's really hard to get right. It's really fiddly. So this algorithm just does what you want it to do. But the question is, what should the return value for something that's traversing a range backward be? Should it just be the iterator? It's not. It's a range. And the reason is because when you're going backwards across the range, you necessarily had to calculate the end of the range. So you want to preserve that information. So this code here does a find last, looking for a slash in this path variable here. And that first one then routes that to a view called drop. So drop drops the first element of the range that's returned, which is the slash, by the way, because find last is going to return you everything. So it drops that, and then I construct a string view and print it. Interesting. Notice there's no loop, there's no iterators, there's nothing to mess up. If I have the case where there's no slash, it just works perfectly. Because I can't be off by 1. I didn't have to write a loop, it just gives me the result. So this is a very different perspective on how to do things. Okay. Everybody with me so far? All right. So let's talk about views. This is the big deal, I suppose. But as I said, the bulk of the library is actually what you just see. So, non-owning. It isn't the case that all views are non-owning, and that's why there's this word mostly. All methods are order 1 for, copy assignment methods are order 1. That's the goal. It's difficult if you have an owning view for that to necessarily be the case. It's going to depend on what it owns. For the large majority of the views, these things are true. Unfortunately, life isn't so simple all the time, and designs aren't so simple. So there are some exceptions. What does this give us? Well, the lazy part of this, the lazy evaluation part, gives us the ability to compose the processing outside of the actual iteration. So first we compose processing, and you've already seen a couple examples of this, and then we drive the actual iteration. Half of the time in the slides that you've seen so far, it's actually the print function that's driving the iteration, and that's under the hood and you don't see it. So this is much more of a functional or declarative style. It takes getting used to. You probably haven't been doing this unless you're a Haskell programmer or some other functional language programmer, or you've seen a Ben Dean talk and you've caught the wave. But it's a much different way of thinking about it. Okay, so let's look at a simple example of a filter view. We haven't seen one of these yet. Again, we have seen one, but here I have a predicate that just checks if something is even, right? When I construct this filter view on the stack, there's no computation that goes on, or there's little computation that goes on. The little bit of computation that goes on is that it finds the first element that actually satisfies this predicate. So it's not fair to say that there's never a computation in the case of the construction of a view, but it's not the overall computation which happens in the for loop. So you'll notice this is a range for loop. Once again, I can't be off by 1. I can't make a mistake. If there is nothing that satisfies the predicate, I get an empty range and I do not execute this loop. Okay. So now, after I have views, I have range adapters. So all of this stuff that you're seeing online about pipe operators, and I've already shown you a pipe operator, this comes from the range adapters. And so really the range adapters are a way to take ranges and create views, and it enables this piping operation and composition. Who programs on Unix, Linux type? Right, so all of you know exactly what the power of a command line looks like and the piping capabilities. So this is the same sort of thing in some very significant ways. So these are all defined in standard ranges views. So here's the equivalent code to the previous code, just rewritten to use the pipe syntax. This is exactly the same as the previous slide in its function. Easy, right? I read it left to right, right? I've got my VI, my vector, which is a range, and I apply my filter, and I construct this thing called evens. Okay? I'm going to show you what that looks like later on, because it's actually a type, right? I didn't write the type here for a very good reason, because it's hard to write that type. It's not an easy type to know. And again, same thing. Okay. So, does order matter? Order matters. Let me ask this question. So now, I've got my vector, and I've got two pipes. I've got a filter, and then I've got a transform, which is another view. Okay? And that allows me to take a function which returns a value. So I'm transforming, the things that are even in this range. And let's see, 0, 2, and 4, if I remember my mathematics, are even in this range. So how many times does the transform actually execute? I got 3 up here. That would be the correct answer. So if you trace the printout here, what you're going to see is that basically the even predicate executes 6 times, 1 for every value in the range, and the for loop only gets entered 3 times, so you only print out the 3 things. Okay. Now, I have to make a comment about views and what they do to constness, especially associated with filter, and I guess caching views in general, of which there are some. You cannot really pass these around by const reference like you might be used to. That's not going to work well. So you're going to want to pass these by forwarding reference. And I want to get derailed into this topic, but this is an important thing to know about. You're going to get some unexpected behavior potentially if you think, that you can pass these by const reference. So why is it that you can't iterate over the filter view in a const fashion? And that's because it caches internally. So it's a non-const operation to do that caching. And that's why. In C++23, the pipe operation and your ability to write your own view mean that if you're really wanting to pass by const reference, if you really want that capability, you could write a non-caching filter view. I'm not saying that's the best answer, but it certainly is one answer. Okay. Composition. This is one of the key things that's happening. You've probably already seen a couple examples where I have something where I'm filtering something and then I'm performing some calculation and transformation on it. But here, is something a little bit different. I'm actually using both parts of the library together, right? This for each here is the range version of the for each operation. So I'm actually using that for each to drive the execution of this view after leading evens. The drop while basically calculates against the predicate and says, drop everything until I find something that's not even. So as soon as I find the first odd value, I iterate over the entire rest of it. Okay? Composition. Ranges compose. Iterators are much more difficult to compose. All right, so here's the survey of all of the views in C++2X. That actually still sort of fits on a slide. So it's a much smaller set. I could have made a mistake. It's possible I didn't get every single one of the 23 views here. We're not going to cover them all. I'm going to show you a couple more examples of views. Some unique ones, maybe. This one is in C++23. It's called Cartesian product. It does what you'd think of as the vector dot product, essentially. So, what have I got here? I've got two vectors. I've got this Cartesian product thing which takes those two vectors. By the way, it's not limited to two. This is a variadic template. If you give it 10 ranges, it'll do the cross product of 10. So you can think about dimensions and how many cross product elements that you want. So this is extremely generalized. And of course, I'm using integers here, and in this case, I'm just printing them out. But you might be running a mathematical calculation. You might be doing whatever it is that you want to do as a result of iterating over this. So once again, you'll notice here in this for loop, I'm using structured bindings to pull apart two values. If I add a third vector here, I have to have a third value in there to get the third vector's value. And you see here, it's just printing out 0, 2, 0, 3, 1, 2, 1, 3. Does this make sense? So it's funny because we used to have a interview question where we asked people about iterating over a multi-dimensional thing for sort of like just this very thing. And now, like, you can write it in sort of like one line of code instead of a spaghetti of for loops. Here's another one, chunk by. And again, you'll see I'm using the pipe syntax here. This one takes a predicate. There's some sister views like chunk and slice that allow you to slice and dice. Again, these now are C++23. Chunk by is very interesting because the predicate determines where the chunks are actually divided. So you can actually divide and chunk up. And again, I'm just getting ranges out of this, right? I'm getting ranges, and the print is just printing those ranges directly. Who's used zip in Python? Yeah, the whole room. So this is a big one, obviously. Zip and zip transform. So being able to put ranges together in a novel fashion, or execute something across multiple ranges in one setup. So here's a few variations of the zip view. So one thing I haven't mentioned, what does the performance of all of this look like in a sense? What's going on with some of this stuff? Well, one of the really great things about what ranges does, and views in particular, is it has an effect where you don't move data around a lot. Basically, you're not moving any data here. You're doing your operation across the original data. It's staying in place. And you're doing the operation, and, well, in this case, we're being very trivial, and we're not doing anything much with that operation. We'll see in a few minutes that there are other things that you can do besides just print them out. Okay, I'm going to stop and pause there. How many people are going to run out and use views next week? Okay, I got a few hands. Okay. Be patient with it. It takes a little bit of time to get used to it. It's a different way of thinking, like I said, but it does pay some big dividends. All right, so let's talk about a few other related topics. Here's span. Span is not in STD ranges, but span nevertheless is a view type. And it's an important view type for contiguous ranges. And it allows you to do some things that, aren't necessarily so easy to do. So, again, it's cheap to copy. It's a pointer and a size. It's meant to go through a by value, pass by value in a set of registers. So the compiler is going to generate highly optimal code, just like string view. You all raised your hands when you said you were using string view. Barely anyone raised their hands when said span. Think about span, because span is a nice way to genericize your code. It's defined in header span, and you can mutate through a span as well as, just access. So here's some simple examples. All of these just work right out of the box. Vector of int, I can wrap it in a span. Notice I have what amounts to a range constructor for, it is a range constructor for the vector. But span also can work with array. It can also work with C-array. It automatically deduces the size of that C-array, by the way. So if I write this function at the top, print reverse, which I don't really need to write because I can just do it with a reverse view, but okay. Span of int, I pass that by value, and I can reverse the view internally, and that's it. It just does what it's supposed to do. And it will work for all of those three other cases. You don't even need to construct it before you pass it to the function. It will just work. It's very powerful. Very powerful capability to work with ranges at that level. It used to be that you'd see a lot of const ref vector of whatever, right? That's the kind of code that people are writing. Well, now we can write code which subsumes that code and does the generic thing without any trouble whatsoever. Span also has a bunch of other things that allow you to get the first part of it, the last part of it, subspan it, do a bunch of other operations. All right, so far we have mentioned that collections and things are ranges, but they're not views. The standard collections are not views, of course, because they're not order one to copy. They're expensive to copy because they're owning ranges, sorry. They own all their elements, and to copy them, you have to copy all the elements. So the views are very interesting and all, but every once in a while, I actually need to get the stuff back out into a collection. I need to take a collection and create another collection. If I wrote a STL algorithm, I would have an output iterator. In that output iterator, I would often write to something. So that's what ranges 2 gives you. And this is a powerful facility that allows you then to express that I want to take the result of a pipeline like this, and I want to put it into a collection. Now you'll notice here that I'm starting with a vector, and I'm ending with a deck. Notice that I didn't have to tell ranges 2 what type to put in that deck. That's not instrumented there, it's not necessary. It figures it out. So, I'm taking the numbers, I'm squaring them, so forth. I'm not doing this calculation, by the way. Well, the type. What's the type of squared? Any ideas? It's a deck of int, that's right. So the deck of int is what you're getting there, and then you're printing it out. So ranges 2 is an important component. This is a C++23 thing. From an implementation point of view, I'm still using range v3 for this particular example. My favorite compiler is GCC, as it turns out, and it doesn't have this facility yet. But the other, at least I believe the Microsoft implementation already has this facility. So here's another example of the same thing, but with a string instead. And I'm using a different view here that I haven't introduced yet called join. And I've created a pipeline here where I'm going to take this vector of strings and I'm going to feed it to this pipeline. And I'm going to put a dash dash space dash dash thing at the end. And unfortunately, my first attempt at this proves that, well, I don't really like that result because, you know, I have an empty string in the last thing there and it looks weird to me. So then all I need to do is make a predicate and reformulate my pipeline over here, putting a filter in front of it, and I get the results that I want. Is there anybody in the room that does not understand what that code is doing? No hands. Everybody's afraid. No. Yeah. Yeah, please go to the mic. Ask a question.
I'm not sure how you get a string out of that pipeline. If join is a view, it seems like you should be producing a range of something, range of strings? Or is it a range of, I don't know, range of characters? I'm not
It's a range of characters. That's why. Right. So it turns out that the view machinery breaks it into a range of characters. You're a brave man to stand up and say that. And it's something that is, for strings anyway, oftentimes a difficulty. Because in some cases, what I really wanted, you know, to process it just solely as a vector of strings. In this case, I'm pushing it all back into a single string, right? So, you know, having it as a char is okay. But ranges 2 is taking advantage of something that is another feature that you can utilize in C++23 when your vendor delivers it, that has nothing to do with the range library per se. And that is a bunch of constructors on every single collection type in the standard library. And these are range-based constructors, range-based assignment, range-based inserts, prepends. Now, you don't get prepend with vector. You only get prepend with the types of ranges that makes sense for efficiently, like list. But these are extremely handy now. Even if you never touched a view, even if you never did anything else, these capabilities are much more elegant than the iterator approach. And this, again, to me, is another example of the kind of thing that is outside ranges as the core library technically, but also very important. Writing a view. I mentioned offhandedly that in C++23 at least, you can write your own view. You could not do that in C++20. Walter Brown, who is here at the conference, is responsible for the recognition that it's very important to allow users to write their own views that compose and are compatible with the standard library. Because the standard library can never, ever provide every single view that we could ever possibly dream up. You guys are smart. You got a lot of different domains. So if you want to write a view that can, you know, work with other things that are off the shelf, you need the ability to do that. So C++23 gives you the ability to do that. There's a thing called a range adapter closure object. It's all very technical. And there's another problem. It just takes a lot of boilerplate, because what is it that you are having to write a view? Well, you don't just write like a view class. Well, you got to write that, but then you've got to write iterators for that view. It's tedious, very tedious. And most of you won't do it. I won't do it. It's too hard. So there is a thing, though, that's coming that's also going to help, and this might be in C++26, But there's a boost library already called STL iterators, or interfaces, sorry. And the idea of this is to take away all that boilerplate and only require you to write the stuff that's actually novel about your particular view iterator. So check it out. If you're interested in doing this, this is an advanced topic. At some point, I will actually have the session, the talk on this, or Zach Lane, who's the inventor of this library, will have this talk. But I think the future ultimately is you write your own view that can plug into the bigger picture. Okay, observation, futures, questions. So one last example for you. This one, this was some code that I was messing around with the other day, and it kind of brought it all home for me what this composition is. And this is actually motivated by a blog post that went way, way back into the 2016 or something like that. So, write the sum of squares. It's a simple thing, right? Just summing up the squares. And, how would you do it in a functional style? And this is basically the code now that you can write in C++23. And so in this first part, I've got two basic functions. Take the square of a thing, add two things together. Those are the two things we need to do operationally. And then I have this iota thing. That's another view. That's an infinite range. Interesting, huh? So I have to stop that range, which is what the take at the end here is. It says take 5 of them from this particular range. And in between, transform it into the square. So the square view basically holds this calculation that doesn't happen until fold left. Fold left is std accumulate, but better. There's also a fold right. There's other variations of it as well. The things that you can think about that std accumulate got wrong, fold left gets right. So I start with 0. That's what the 0 value is there, and I do an add, and I get a total out. Very simple. And, I can use this enumerate thing over here. So I wanted to enumerate all the actual solutions. That I can do with now also a single line of code. It's a very different way of thinking about things, but once again, you'll notice there is not a single loop on this code. Now, Sean Parent and some other people have made the statement, I think even John Kalb have made the statement, we should be writing loopless code. There should be no loops. That's been very, very difficult to do, in my view. But I think we're getting closer. C++26, it's not going to stop. This is the proposal set, subset of the proposals. There's actually this paper that's linked at the bottom, the 2214. This is the plan that people are working towards. So there's a whole nother set of things coming here that make this library allow you to do even more than you can already do. I don't think we need C++26. I think C++23 gives us the base set. And especially with the ability to write views that will be compatible with the standard, we have a way forward. So here's my advice. Always use range algorithms first. They're better constrained. They have better return values. You can use projections. You'll get better, superior results. No one can tell me there's going to be an optimization problem with those algorithms. The fact that you moved begin end into instead of writing it up here doesn't matter one bit to the compiler. It's the same thing. Use view adapters. View adapters are really where it is. I think of views and view adapters at this point sort of interchangeably. I don't really think of them as different things. Don't be evil. Don't write garbagey pipelines that are impossible to understand. I've seen, certain unnamed members. I've seen all kinds of bad pipelines displayed to me where I couldn't follow anything with what they're doing, right? So this is a facility. It's a tool. It can be used well, and it can be used badly as well. So that's my advice. So final thought is that I think there's no question in my mind that ranges is a key abstraction. Even if you don't use views, even if you excluded that whole thing, ranges as an abstraction and a capability is really important. And we're going to see a lot nicer code, more capable code. Constrained algorithms is also an important thing. And I think we're still at the beginning. The survey of this room means that we're still at the beginning. You guys haven't started utilizing this fully yet. All right, do we have questions? We have a few minutes left. Yeah, if you've got a question, you should come up to the microphone.
Do you know why std accumulate didn't make it to ranges views?
Why std accumulate didn't make it? No, well, I know because it was just a time problem in part. Fold left is the replacement for std accumulate.
I noticed in your example, you didn't pipe it with the rest of the transform. You had to use it on its own.
That's because it's an algorithm and it's not a view.
So does that mean it cannot be lazily evaluated?
That's correct. It is not lazily evaluated. So again, the square view is lazy. The fold left is not. That's what's actually executing the entire pipeline.
Thank you.
Yep.
Yeah, could you go back to the slide where you created the string? It was also, you had the join example. Yes, yeah, and thank you very much. Great talk, by the way. So just a couple questions here. So getting further into the previous guy's question. So I would assume that at the RV filter stage, at that point, it's still a range of strings. Is the join the thing that turns it into a range of characters?
Let's see.
Because the is not empty actually directly takes a string as an argument. So it seems like it kind of has to be.
Yeah, the join is flattening.
Okay, cool. And then my follow-up question was just for the two there, I'm just kind of curious how that's actually done. Is that just like a pushback call? Obviously it's got to be done in a generic fashion. And so I'm just kind of curious. It seems like it supports STL containers generally. So I'm just wondering what the generic approach is that's taken.
So it supports ranges generally, not just STL containers. However, for efficiency reasons, those other overloads of things like append and so forth were added to the containers to make this be efficient.
Okay.
Yeah.
Thank you.
Mm-hmm. Over.
Thank you for the talk. I actually had the same question as the gentleman. So.
Okay. All right.
Going way back to range adapters.
Yes.
In that slide, I didn't see something called out as what is the adapter? I mean, I saw, views and filters or whatever.
Let's see. I skipped over the type slide somehow. Where were?
I think the views from ranges. So
okay. Yeah. So let me just clarify. So if you saw the original slides, there was a, filter view, right? Okay. So filter view is in namespace ranges. If I take the view off of it and go to the view namespace, there's a thing called filter with no view on the end of it. That's the adapter that makes a filter view, and the adapter doesn't have the view name on it, but it's in the view namespace.
Okay.
That's how you know the two are different.
While listening to your talk, I was remarking on the power of the pipe operator for composability.
Yeah.
Something I've always wanted was to be able to kind of specify my entire server architecture as a series of stages composed by pipes.
Yeah.
How close or far we are from specify an entire program server as a range?
I think we're far, would be the simple thing. The slide I actually skipped over may be actually relevant here. So on this slide, basically, I have a view chain. And so the question is, what's going on under the hood here? What are the types? So I skipped over the magic thing that, puts out the type name. But as you see here, I take a join view and I put it around this vector of strings. And so what do I get? I get a join view of a ref view. The ref view is there because it's the machinery of ranges to reference a view without, and then I get my vector. And if I put a take view around that, then I get another type around it. So I'm building this chain. You could possibly compose a server that way. I think it's a hard ask.
Well, thank you.
Yep.
So you talked about when constructing a view, how it's not entirely no operations, how sometimes,
Right.
Is that required by the standard or is that an optimization? And then also, does that happen to all the views or just the particular filter view?
Right, so the caching is something Nico, who's sitting in the back, has talked a lot about. And it's controversial, I guess I'll say that, at least. And so, but yes, the wording basically is requiring that because the order of operations, the future operations essentially is requiring that the way it's written.
There are two parts to what I wanted to ask. The first is at the beginning when you were asking who had used ranges, I didn't put up my hand because I only looked at using ranges, not because my target compiler wasn't supporting them very well,
Yeah.
as the Apple claimed.
Ah,
And I looked around and I was trying to see if there's an alternative I could use,
Yeah.
or platforms that didn't, where the compiler didn't support it.
absolutely. You can use range v3 right now today. It's a C++ 14 library.
Oh, really?
And range v3 is the prototype, if you will, for the standard ranges. It's what most of the things are based on. Even if you look at what's proposed for C++ 26, you'll see that most of those are coming from range v3.
I looked up there and I saw it was marked as experimental usage only. Was I maybe looking at the wrong sort of thing? Or
I don't know. I used it in production.
okay.
Listen, I'm a wild man. I do this stuff, and when it just all works and it runs fast and there's no problem with it, then I'm okay with it.
Okay, the next question is, where does sorting fit in all this? Sorting.
Sorting?
Yeah.
Yeah, so sorting is a range algorithm, and you can use it.
So is that we pass it a list? Is that creating a new sort of range,
If you pass it a list, sort will reject you.
or
Because you don't have the proper properties. Just like if you try to pass a list to sort standard STL sort.
Yeah, I misspoke there. I meant a vector.
Yeah, if you pass a vector, like that was at the very beginning of the slides, which I don't want to go back, it just works. You just pass your collection right there and it just works.
Is it sorting the vector in place, or is it creating a new one?
It's doing the same thing that std sort is doing. It's just taking the begin and end from your collection and using that begin and end instead of you writing it. It's the same thing, basically.
Okay, thank you.
Yeah. I'll get back to you in a second.
Hi, thanks for the talk. It was really good. Okay, so you make a nice, clearly laid out chain of piped operators. Doesn't work. How do you debug it?
Good question. How do you debug anything in C++? You look at the horrible compiler errors and you gasp and
No. So it compiles, but it doesn't give you the answer that you want.
Oh, that's interesting. Well, my personal advice would be break it down into smaller pieces and test each one individually. You saw a lot of very small code here that was like obviously true. Like you didn't even need a test case for some of those kinds of things. So that would be my recommendation. There's no great answers. Yeah, second Question?
Well, so now I'm thinking I have a crash dump. I can't change the code.
Okay, well, you'll see all the output. Yeah.
Thank you.
Yeah, over here.
Hi. You had said to not pass the views as a const ref, instead pass it as a forwarding ref. But why not just pass it as a non-const ref?
You could do that, but the forwarding ref is actually going to, otherwise known as a universal ref in some quarters, that's going to do the best thing for you, basically. Okay, so that's going to bind in the best possible way. And so if you look at any of the ranges, signatures, and so forth, you'll see that that's the way that all of the ranges are passed into the algorithms and so forth. So, yeah.
Hi. I think you probably partially answered this already with the comments on list, but it's kind of complicated to write your own range algorithms, but what constraints are placed on writing your containers to pass into the algorithm?
Right, so what constraints are on any given algorithm are going to depend on what the algorithm does, right?
So you have to have traits that...
Well, so we really kind of flew over, and I think my clicker might have gone over a couple slides too quickly or something, but if you look at the concepts that are in the standard, okay, you'll see that the various operations, the various algorithms in the standard are constrained in different ways. So you've got, contiguous ranges, you've got all of the things you would think about in the past with the iterator model, with the range model now. So we have bidirectional, we have some other new things that are maybe a little different that weren't in the iterator model, and you can constrain your algorithm and your overloads to take only that set and otherwise give an error, or as it were, spine away, right, so that they're not part of the overload set, which if you don't have one that works, will end up in an error.
Thank you.
So similar question to the const reference input to a function just now. So let's say if you accidentally pass const reference as an input, what kind of the exact bug that you may see from doing that?
I'm sorry, I didn't get the end of that.
Oh yeah, so let's say if you accidentally pass const reference of range into a function, what kind of bugs would you see? What kind of issue?
Right, so the question is, what kind of bugs will you see if you pass by const ref? You might not see anything. It depends on what kind of range you pass in, and I think this is part of Nico's point, is that it's very ugly to see that, oh, I had this function and it seemed to work fine, and then I put a filter view in front of it and suddenly it doesn't work fine anymore. And so, yes, there's that complexity. If you're going to write function overloads that are going to take those ranges, something important to know. So the session is over. I will be available afterward to answer more questions that anybody wants. Thank you very much.